All right, so we're going to apply what we've learned about differentials to an idea of approximating error. So if you have a function, y equals f of x, if this is some real-world application, then what you might be doing is taking a measurement of a value x. So you measure some quantity x, right? And then you take that and you put it as an input to a function, and then you use it to calculate the resulting output quantity y. Right? So you measure x, and then you use that to calculate y. But when you take a measurement, often there'll be some error. So like, let me pull up my ruler here. If I measure something in centimeters, I can probably only measure down to about 1 millimeter accuracy, right? Like it's hard to actually measure something with finer accuracy than in 1 millimeter. Sorry, I said accuracy, but I really mean precision. We can't measure any more precisely than 1 millimeter. So that means that our measurement could probably be off by as much as 1 millimeter, or maybe it could be off by as much as like half a millimeter, either like more or less than the exact value. So your error, so that is like a change in x, right? You can think of that 1/2 millimeter as like a little like change in the x value that could actually be there, right? We could be off by that much. So we can think of dx for applications as representing an error in the measurement of the input, x. Then the dy will be an approximation of the resulting error in the calculated value of y. So what I mean then is that like the max error in the function value f of x resulting from this error in the input value, that'll be approximated by dy, which is f prime of that measured x value times the dx, which would be the maximum error. So this is a nice kind of quick, easy formula for calculating an approximate error in your output value. Also, occasionally, we'll discuss the idea of maximum percent error, and percent error just means that you're going to take your error and divide by the overall value of the function. So that's, instead of just dy, it's dy divided by y. So that would be like f prime of x times dx, and then divided by f of x. So whether you're dealing with max error or max percent error, you use this formula here, dy equals f prime of x times dx. So let's do an example of this. Let's say that you are trying to calculate the volume of a sphere. The formula for that, by the way, is 4/3 times pi r cubed, where r is the radius. Let's say we take our sphere here, and we try to measure the radius there. And measuring the radius of a sphere is kind of hard to do because, where do you put your ruler, right? Like, you kind of have to use something called calipers, where you come along and you kind of measure the diameter by doing something like this, and have these be parallel to each other, and then here's your ruler, and you can measure the diameter like that, and then just cut that in half and get your r. Okay, so we come along and we use our calipers and we measure the diameter to get the radius. And let's say we measure it as radius is, I'm going to use the math I've got here in my example, some tiny amount. This is a really small sphere. Radius is 0.5 centimeters, but with a possible error in that measurement of 0.01 centimeters. Okay, this is 1/100th of a centimeter. This is like 1/10 of a meter. That's pretty small. So these are some very accurate calipers that we're using to measure this. Okay, so what that means is our r is 0.5, but our dr is 0.01. Okay, we have two independent variables here: the measurement itself and also the possible error in that measurement. And that, by the way, that could be plus or minus. So what I mean by that is, like, it could be 0.51, or it could be 0.49, right? It could be that we're off either above or below. We like too much or too little. That goes both directions. So now, if we calculate the volume right here, right, then that volume calculation could be off. But how much could it be off by? Well, the change in volume occurring from this change in R is going to be approximated by our dV, which we can get by just taking the derivative of the volume, differentiate that volume real quick. We're going to get 4 pi r squared, and then multiplied by dr. Okay, so that's the formula. That's this formula right here. So now let's calculate that value with our specific numbers. So in this case, we're going to have 4 times pi times 0.5 squared, and then times 0.01. All right, and that ends up being approximately 0.0314. And since we have, this is centimeters, and this is also centimeters, that's going to be centimeters squared times centimeters again. So this is centimeters cubed. That's our approximate, that's dV, right? So that's our approximate change in volume. So that's like an approximate error in the volume calculation. So let's compare. We're saying that the radius could have been off by as much as 1/100th of a centimeter. But the volume we calculate, given that measurement, could be off by closer to like 3/100ths of a cubic centimeter. Okay, so that increased. That's bigger. And whenever you're doing a calculation where you're taking like a measurement and then you're increasing the dimension, so like you're taking a one-dimensional measurement and then calculating a three-dimensional quantity like volume, whenever you increase the dimension, the error sort of compounds, and you get a bigger error in the output, which is what we're seeing here. So that's our error, an approximation of the error, because this was a differential, not the actual delta V. So now we can also calculate the percent error, by the way. Percent error, this is going to be approximated by dV over V. So that would be our, our 4 pi r squared dr over the original volume formula for thirds pi r cubed. And if you take those, all of our numbers, 0.5 for r, stick that in, and 0.01 for dr, and stick that in, this ends up being approximately 0.06, which is 6%. So this error in the measurement could produce a 6% error in the output calculated value of the volume, which is not insignificant. 6% is kind of a lot.